So in this video, we'll be looking at heat transfer in conduction. So now when we talk about conduction, we're referring to the rate or the form of heat transfer which involves two solids or two metals. So now the difference is that the difference between the conducting and then convecting or the radiation is that with conduction it involves only solids or metals. So there is no fluid or there's no gas present. So now you have a question that says that the roof of an electrically heated home. Now this roof indicates that it's a solid, right? So the roof of an electrically heated home is 6 meters long. So let's just give a sketch. So we have a sketch of the roof. It is 6 meters long, 8 meters wide, and 0.25 meters thick. So now we have a thickness here. It is 0.25 meters thick. It's made of a flat layer of concrete whose thermal conductivity K is 0.8 watts per meter Kelvin. The temperatures of the inner and outer surfaces of the roof one night are measured to be 15 degrees Celsius and 4 degrees Celsius respectively. Now, the inner of the roof is 15 degrees Celsius, then the outer is 4 degrees Celsius respectively for a period of 10 hours. Determine I the rate of heat loss through the roof. So now, because we have our roof this way, and then it's a solid, it has a thickness, right? And then the inner of it is 15 degrees Celsius, and then the outer is 4 degrees Celsius. Now, because the inner is 15 degrees Celsius, and then the outer is 4 degrees Celsius, then for a period of about 10 hours, so even just for 2 seconds or very short time, heat will be transferred from the hotter side to the colder side so as thermal equilibrium to be established. Now, the moment we know that we are dealing with conduction, then the only approach we can use to solve is resorting to the Fourier's law of heat transfer, which states that our K of heat is equivalent to K multiplying our area of heat transfer multiplying T2 minus T1 all over our thickness. Now our T2 here is now our hotter body, our hotter temperature. Our T1 here is our colder temperature. Okay. So from this diagram, it means that our T2 here becomes 15 degrees Celsius, and our T1 here is 4 degrees Celsius. Now we have our thickness to be 0.25 meters, and then our length is 6 meters, our width is 8 meters. So now to find the area, we know that area is length times width. The area of the heat transfer will be across this roof. So now this is the roof. We are looking at the surface area of the roof. That is length times width, which is 6 meters times, 8 meters times 6 meters. That gives us 48 meters squared. Now with the thickness, now when we look at the roof, the inner part of the roof is 15. So it's going to transfer from this inner side to the outer side. It's going to be transferred across the thickness line. So now our thickness becomes 0.25 meters. And then we have our thermal conductivity to be 0.8 watts per meter Kelvin. Let's just do substitution. Our K is equal to 0.8 watts per meter Kelvin. I want us to put in the unit so that we can know the actual unit for the K that we are finding. Our area is 48 meters squared. Then our T, change in T is 15 degrees Celsius minus 4 degrees Celsius. Now, because we are dealing with change in temperature, whether the temperature is in degrees Celsius or Kelvin, we still get the same answer, right? So we can just read it out and say Kelvin, all divided by our thickness, which is 0.25 meters. So Kelvin cancels Kelvin here, meter square, and this meter cancel out. So now we are left with Q being equal to 0.8 watts times 48 times 15 minus 4, all divided by 0.25. Now, Inputting this on the calculator, you're going to get 1690 watts. So now this is our rate of heat loss. You know that when you say rate, it's per time, right? So and then our watt is joules per time or joules per second. So now this becomes our rate. So this is our I. Now it's our I. Or we can even say Q is equal to 1.69 kilowatts. With our II, the cost of that heat loss to the homeowner, if the cost of electricity is $0.08 per kilowatt hour. So now we are saying that one if 1 kilowatt hour costs $0.08, what will be the cost for 1.69 kilowatt 1.69 kilowatt. And then this one is in hour, and then ours is in kilowatt. We have to convert this into the hour form. Now to get it into the hour form, we have to multiply by the time. So our kill rate is equal to 1.69 kilowatts times our time t. Now our time was for 10 hours in the first thing. We have 10 hours here. So 10 hours. Now to get the heat rate, we are going to say 1.69 times 10 hours. And that gives us 16.9 kilowatts hour. So now, if 1 kilowatt hour is equivalent to $0.08, 16.9 kilowatt hour will definitely give us more. It's going to cost more. So if more, let's divide 1 kilowatt hour 16.9 kilowatt hour times $0.08. Now we get kilowatt hour cancels kilowatt hour, and then we are going to get 16.9 times 0.08. We need to get $1.352. So now this becomes our cost for the heat, the rate of heat loss. Yes, so our final answer becomes $1.352. So this becomes the end of the video. Please subscribe and share.